All right, this video is going to be about the mean value theorem, and this mean value theorem comes up by name. There's not a lot of things that we really need to memorize by name, but the mean value theorem is definitely one of them. So make sure that when you see the phrase mean value theorem, you know that it refers to this. In the mean value theorem, I really like to think of as almost like the mean value formula, because that's how we use it most often. The mean value theorem says if y equals f of x is continuous at every point on a closed interval and also differentiable at every point on the inside of the interval, then there's at least one point C in AB at which f prime of C equals f of B minus f of A over B minus A. So basically, long story short, it says that if you take the y values of the endpoints and subtract them, the x values of the endpoints and subtract them, what you're really getting here is you're getting the average rate of change, or basically the average slope of a graph. And this right here says you're looking at your instantaneous slope of a graph. And at some point in between A and B, that average rate of change equals the instantaneous rate of change, all right? So what's important to understand about this is a couple things. One important thing is that differentiability must hold. Differentiability, if I could spell, there we go. Differentiability must hold for the mean value theorem to be true. What does differentiability mean? What does it look like? Well, it means that something has to be able to take the derivative, and you can only take the derivatives of graphs that are both smooth and continuous. So you can't have any pointy corners, you can't have any holes, you can't have any asymptotes on the interval from A to B. So you have to be smooth. So here's a perfect example. Here is a smooth curve from A to B. This dotted blue line here gives you the average rate of change, or the slope of this line is the average rate of the change of the function between A and B. And then this blue line up here is a tangent line at a specific point. So here's the instantaneous rate of change of the function at C. And what you see from this is the secant line and the tangent line are parallel at some point in between. It's not parallel all the time, but there is a point in between A and B such that the secant line and the tangent line are parallel. So the mean value theorem guarantees that if f of x is differentiable on the closed interval from A to B, then at least one point C on the open interval from A to B, the tangent line is parallel to the secant line. And it's very important, the value of C must be on the open interval, so C cannot be one of the endpoints. Now, the endpoints may have the slope you're looking for, but they're just not guaranteed, they're just not covered by the mean value theorem. So long story short, all this stuff that I keep saying many, many words about really boils down to this. At one point within an interval, the instantaneous rate of change is equal to the average rate of change for the function. All right, instantaneous and average will match up at some point on the interval. All right, so examples will often say, apply the mean value theorem to this function because we tell you to. So here's how that works. If I look at this function, I have to first decide whether the mean value theorem applies. So is a cubic function continuous and differentiable on an interval? Well, yeah, any interval. A polynomial is always continuous and differentiable, so no worries there. So if I'm going to use the mean value theorem, I'm going to write it as a formula. F prime of C has to equal f of B minus f of A over B minus A. So now I'm going to set it up. F prime of C means take the derivative and then plug in C. So my derivative, f prime of x, is 3x squared minus 2x minus 2. So f prime of C would be 3c squared minus 2c minus 2 equals f of B minus f of A over B minus A. So that means f of 1 minus f of negative 1 over 1 minus negative 1. So I have 3c squared minus 2c minus 2 equals, now f of 1, I come to the original, it says f would be 1 minus 1 minus 2, which would be negative 2. F of negative 1 is going to be negative 1 minus 1, which is negative 2, plus 2, which is 0, over 1 minus negative 1, which is 2. So 3c squared minus 2c minus 2 equals negative 1. I'm going to bring this guy over, solve for c. And oops, pardon me, if I add 1, this is going to now be a minus 1, not a minus 2. Let me fix that here. And now I can factor this, so I have 3c and c. I'm going to definitely have some 1's here. This has to be a minus and that has to be a plus. Those are both equal to 0. So I end up with c equals 1 and c equals negative 1/3. So these are potentially the values for c guaranteed by the mean value theorem. Well, only one of these matters because I'm on the interval from -1 to 1, which means I can only pick values in between those, and the only one that's in between is negative 1/3. Okay? All right, let's flip it over. All right, so for our next one, we have f of x equals x plus 1 over x on the interval from 1/2 to 2. So the first thing I'm going to notice is, whoa, 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 this is not a continuous function across its entire domain. X isn't allowed to equal 0. But that's okay because my interval doesn't include 0. If this said negative 0.5 to 2, mean value theorem wouldn't apply and you'd just say, nope, doesn't apply and move on. However, since 0 is not on the interval, the mean value theorem does guarantee a point. So what we're going to do on this one is we're going to set up basically the mean value formula. But before I do that, I'm going to remind you that to take this derivative, I'm going to rewrite f first as 1 plus x to the negative 1, which makes my derivative way easier to take. So f prime is just negative x to the negative 2. So f prime of c would be negative 1 over c squared equals f of b, so f of 2. Well, 2 plus 1 over 2 is 3/2, minus f of 0.5, so that'd be 1.5 over 0.5, which is 3, over 2 minus 0.5, which is 1.5. F of b minus f of a over b minus a. So 3/2 minus 3 is negative 1.5. Divided by 1.5 is negative 1. So negative 1 over c squared equals negative 1. So c squared equals 1. So c equals plus or minus 1. Now I'm going to check my interval. Negative 1 would not be included, so I'm just going to keep the positive value. Okay, now we just solved for c twice, and I didn't really talk about what it means. Here's what it really means. Now, I'm going to press pause for a second. What I want you to do is I want you to graph this function on your calculator and zoom to a window from like 0 to 3. I'm going to do the same thing, but it takes a while. So hit pause, graph that, and we'll come back to each other. All right, so here's the graph of that function on the interval from 0.5 to 2, and I'm going to do something fun because I can and my computer's special. Whee! Look at that. So here's the graph. Here's the function. And if I plot the point 0.53, which is right about there, and the point 2, what was it, 1.5, which is right here, and I connect those with a straight line, that's a straight line with a slope of -1. Now, I know it doesn't look like -1, but we've gone down one y value, basically, one at a time here. So I've gone down 1.5 y's and 1.5 x's, so my slope is -1. What this c is saying is if I plot the point for x equals 1, the slope at that line matches, the slope at that point matches the slope of my secant line. So at c equals 1, if I were to draw the tangent, this tangent line is parallel to that secant line. All right, so we've got 3 here. Square root of x squared plus 1. Little thing I want to talk about, square root of x squared. I know in your little brains right now, you're like, oh, squares and square roots cancel. Well, kinda. The square root of x squared is actually the absolute value of x. So this is really the graph of y equals the absolute value of x plus 1. But absolute values have a v in them, right? So this graph looks something like this. Is that graph differentiable on -1 to 1? No. So we can't do the mean value theorem. So the mean value theorem does not apply because the graph isn't differentiable at x equals 0. So I don't even have to do the mean value theorem. Done. Easy peasy. And these last two are really examples of why do we even care about the mean value theorem? How does calculus apply to my real life? And, I'll be honest, and I'm always honest with you guys. 95% of you, calculus doesn't matter. But these are examples where it does. A plane begins to take off at 2 p.m. on a 2,500-mile flight. It arrives at its destination at 7:30 p.m., assuming no time zone changes. So we are flying, let's say, just straight south. Explain why there were at least 2 times during the flight when the speed of the plane was 400 miles per hour. All right. Well, let's see. We have a 2,500-mile flight, and it took us 5.5 hours to get there. So if I take my calculator and I do 2,500 divided by 5.5, I'm going to get 400, was it 454? I think it was. 454.54 repeating. What is this number? Well, that number is distance divided by time. This is the average speed. This is the average rate of change for the function that models my flight. So if my average speed is 454 miles per hour, then, well, if my average speed is that, why do I have to go 400 miles per hour? Well, the plane has to take off and then land, and you didn't take off going 454 miles per hour. So you had a speed of 0 when you started, you had a speed of 0 when you landed, and your average speed is 454 miles per hour. So that means you had to go from 0 miles per hour, get up to 454, and then get back down to 0 miles per hour. There's 400 miles per hour in between there. That's a theorem that I know you talked about last year in pre-calc, and that's called the intermediate value theorem. So if you were to answer this question, you'd say, well, the average speed of the plane is 454 miles per hour. And since it starts and lands at 0 miles per hour and gets up to a speed of 454, a speed of 400 is guaranteed by the intermediate value theorem at least once before and once after it reached that average speed of 454. You could also argue that you know that the speed goes above 454 miles per hour because if you average that and within that average you have zeros as well, then you know you had to go higher than that for that to end up being your average. But really, long story short, average speed is distance over time, and your intermediate value theorem guarantees that you hit that at some point. All right. Car uses the Easy Pass system on the New York State Thruway. Car enters the Thruway at the 490 exit on the Thruway that's at milepost 350.99. Yes, I looked this up, by the way. It then exited the Scotia exit at milepost 162.22, 2.5 hours later. All right, so let's see. How far did they go? They went 350.99 minus 162.22, and it was 2.5 hours later. So I'm going to divide by 2.5. 350.99 minus 162.22 divided by 2.5. 75 point something, we'll write ish, miles. Not miles, pardon me. 75 something miles per hour, because this is miles, that's hour, that's miles per hour. This is my average speed. All right, if you hear that alarm, it's my alarm to remind me to get my son. Hold on. Okay. This is my 75 miles an hour. That's my average speed, okay? Now, the mean value theorem guarantees that at some point my instantaneous speed has to equal my average speed. So if my average speed was 75-ish miles per hour, that means at some point my actual speed was 75 miles an hour. Am I allowed to go 75 miles an hour on the Thruway? No, I'm only allowed to go 65 miles on the Thruway. That's why, if it were legal, I don't think it is right now, but if it were legal, state troopers could totally send me a driver a ticket, send me the driver a ticket in the mail for speeding. Because they know I average 75 miles an hour. That means I was going more than 75 at some point, and at least 75. So they could totally send me a ticket and say, you were speeding, we've taken calculus, busted. Also, take a second to appreciate the joke. Why did the chicken cross the road? Because he's the intermediate value chicken, and he has to. If he started at f of a and gets to f of b, he's got to go whoop at some point in between. Wonderful. I hope you've enjoyed our little lesson here on the mean value theorem and why you shouldn't speed and why you should always wear your seatbelt. So no speeding, wear your seatbelt, no calculus, and you're a happy camper. I hope you're all having a wonderful day. See you soon. Bye.